So I'd like to talk about elliptic curves over the rationals. So fix an elliptic curve E, and what I'm going to show, or what I'd like to show, is that there are infinitely many cyclic extensions of degree 6 of the rationals, such that the Mordell-Weil group has a new point. And by a new point, I mean not in the subgroup generated by any of the subfields. Okay, so the question is whether or not that happens infinitely often, and we show for this situation that it does. If there is such a point, then we know by Kato that the L function associated with the elliptic curve has to vanish at a character of order 6, and that the rank is at least 2 of the Mordell-Weil group. In a paper by Berg, Ryan, and Young, they did a random matrix theory prediction of how often you should expect central vanishings of such L functions. That is, associate L functions, the L function of E twisted by characters of order 6, the Hershy characters of order 6, and say conductor less than X, and they say from random matrix theory that should happen about X to the 1/2 some power of log X times. And just for certainty, we know that the number of characters of order 6 with conductor less than X should be of the order of X times log squared X. Okay, so about that many vanishings should occur. They're rare, and they're 0%. 100% of the times the L function should not vanish. For certain families of elliptic curves, we actually prove that we can get very close to the conjectured random matrix bound. We show that we actually construct fields which have conductor less than X, and we approximately root X of them. At least, sorry, not at least root X of them. Okay, so the idea is to try to describe points on extensions of degree 6 by finding points on a higher dimensional variety over Q. And the variety that we have in mind in this case is E, it's a surface, E cross E, and we divide by an automorphism of order 6. The automorphism here is given by this thing P, a pair PQ goes to Q, P minus Q, that has order 6, and it's defined over Q. So the variety itself is defined over Q, and its Q rational points should be telling us about points on cyclic extensions of degree 6. Okay, the geometry of this particular variety, I will briefly say. The group of order 6 acts freely on all of these points except for a set of order 20 of size 24, consisting of pairs of torsion points of some sort. And the result, if we have a point, a rational point on this surface after we take away these 24 bad points, if we have a rational point, square brackets PQ, that corresponds to one of these 4 situations. Either both the points are defined over Q, they're both defined over a quadratic extension, the same quadratic extension of Q with a particular Galois action, cubic fields, the cyclic cubic field with a particular Galois action, or the 4th one is the one we're interested in. They're both defined over a cyclic sextic extension. Okay. It turns out that a minimal non-singular model of this surface is a K3 surface whose Picard number is either 20 or 19, depending on whether or not he has complex multiplication or not. We don't actually ever use that. We just use the surface, the affine points on the surface. And a lemma that we prove is that if we have a rational point on the surface such that the point P, or one of the two points defining the equivalence class, is in a cyclic sextic extension, if it has infinite order, then it has to be in a subgroup. It's not in any subgroup generated by proper subfields. So it's a really new point. Okay, so that's a technical little argument that we make. It depends only on the action of the Galois group on the points of our surface. Okay, so the way we actually find these points is we can realize if we take E, a Weierstrass equation for E of the form, this form here, the usual one, short Weierstrass form, then we can write down an affine model for our surface given by these equations. The way we get it is by intersecting points with lines, and there's an argument we have to get it. The thing to notice here is that for fixed T, this is the fiber over T is an elliptic curve. Okay, so we use the in U. Okay, in D and U. Okay, it's quadratic in D here, D squared, and U cubed, and so on. Okay, and so that gives us a handle on how to construct points if we get started. Okay, and if we find a Q-rational point on the surface, then the point P on the curve that we get, so remember a point on the surface is a pair, PQ, the equivalence class of a pair. So the point on the surface, if it has if it has coordinates X and Y, the X coordinate satisfies this cubic, and the Y coordinate is a sextic, which is obtained by taking the square root of an element in the cubic subfield. Okay, so a cyclic sextic is always made up of a cubic subfield and a quadratic subfield. Okay. So the X coordinate lies in a cyclic cubic subfield extension of Q, and the Y coordinate is you get by taking the square root of some element of that. Okay, so the main result, the way we get it, is we notice that if E is an elliptic curve over Q and ED is a quadratic twist by, say, the rational number delta, then the two K3 surfaces we get for E delta and E are isomorphic over Q. Okay. And then the main theorem is that if E is an elliptic curve over Q, if we choose a delta, which is a twist for which the rank of the elliptic curve, the twisted elliptic curve, is at least 1, that is, if it has infinitely many points, then there are infinitely many cubic extensions of the quadratic field Q root delta, such that that cubic extension is a cyclic extension of the rationals of degree 6, and for which the rank of that cyclic extension, the rank over that cyclic extension of our elliptic curve, is strictly greater than the rank of the subgroups generated by all the subfields. So that gives us our new point. Okay. Okay. I mean, it's based on a previous theorem that Kawada and I were able to prove when we studied cyclic cubic extensions of Q and points of rational points on the elliptic curve over cyclic cubics. But there we weren't able to prove that you always get cubic twists which have points. However, in the case that the base field had a point of infinite order, then you could prove it. Then we proved that there are infinitely many cubic twists that do have points of infinite order. And so we use that fact on the twisted, the quadratic twist of our original elliptic curve to get, now that our quadratic twist has a point of infinite order, we can produce a point of order, of infinite order on the sextic twist by using this. So the way this works is that the cubic twist, the set of cubic twists, so the set of cubic twists here, this is a double cover of the surface giving us the sextic twists. And since the cubic twist of E delta has a point of infinite order, then the sextic twist of E delta has a point of infinite order, gives us a point of infinite order. And since the sextic twist of E delta and the sextic twist of E have the same surface, then you end up with a point of infinite order always on the sextic twists of E. Okay, so let me give you some examples. So this is basically the argument. So let me look at a special case. Suppose E is a curve which happens to have a rational 3S orogeny. Then E can be written in this special form. And the surface is given by this expression. So it's the same expression before, except we're using these A and B's for the parameters. Okay, what's nice about this is if we take T equals B, then the surface has a very, very nice form. Okay, and the affine model here is a parameterizable curve. So we can give points on the on this surface by this formula here, where S is a rational variable. So every value of S gives us a point on this surface. That should be SE S6 of Q. That's a Q bar. Okay. If PQ is the corresponding point for the image of S, then the x coordinates of the points P or Q in the on the surface satisfies this cubic extension. Okay, and the y coordinate satisfies this particular equation. Okay, so we have equations, we know the fields in some sense, that the point P is defined over. And so I want to get an estimate on how big the conductor is for that field. That gives us a count on how big the conductor is for the sextic character. So we let S be a quotient of M and N, say, and write X in this form. And X, this X prime, is a root of this equation now, which has integer coefficients. This equation is it's Eisenstein at m squared plus 3n squared. So it's irreducible. It's a reverse Eisenstein. So it's irreducible. And so we can write the discriminant. We can compute the discriminant, and we get the discriminant here, and there's our factor, m squared plus 3n squared, which corresponds to the ramification at m squared plus 3n squared. Okay, so the discriminant has a very concrete form. So the discriminant's a square. We know that the root is in a cyclic extension of degree 3 of the rationals, or of Q of mn in this case. And generically, no. I eventually will, yeah. As a generic polynomial here, it's Eisenstein. This has, if you think of this as a polynomial, yeah. So it's generically reverse Eisenstein here. And when we specialize, we're going to specialize to square free numbers. So it'll be Eisenstein at any prime dividing one, which I say over here. Okay, the factors dividing m and n turn out to be extraneous factors in the discriminant, and they do not represent ramified primes. So I think there's a name for that in German. But. Okay, so the x coordinate lies in a cyclic extension of degree 3, whose conductor divides the square root of the discriminant, and so it's a factor of this. Okay, similarly, the y-coordinate, when you calculate the y-coordinate, it lies in this field. And that integer there is generically coprime to m squared plus 3n squared. Okay, and so so then it will also divide the conductor, because anything dividing that will ramify if it's square free. And so this is a cyclic extension. K, if you join both the x and y coordinates for that m and n, is a cyclic extension whose conductor will be a divisor of this this form. Okay, so that's the degree 4 form in m and n. Okay, up to a finite number of factors. And there's a result going back a number of years to Stewart and Top that gives an estimate that says the number of distinct square-free values of a quartic form like that is the number of values less than x of such a quartic form is at least constant times root x. Okay, and so we end up with saying that the number of sextic fields with conductor with a point of order coming with a point on the field of degree 6, not coming from a new point, not coming from a subfield, happens for at least as many fields as we have conductors. Okay, there might be more, but at least as many fields as the number of distinct conductors. And we know that the number of distinct conductors less than x is at least constant times root x. So the number of vanishing twists, I'm going the wrong way. So the number of vanishing twists of this particular family of elliptic curves is at least root x, which is within a power of a log of the random matrix prediction. Okay, there are other families for which the same property holds. In general, we can't prove that it's true for any elliptic curve, but at least we can show that you have infinitely many vanishings. Okay, I think that's all I want to say about this.